Okay, so yesterday we introduced the topic of organic chemistry. We talked about what constitutes organic compounds, and those are compounds with a carbon base, but more properly, carbon and hydrogen to begin with, right? Uh, we might come across some compounds later that have been reacted and modified to remove the hydrogens and replace them with some other elements, atoms or some other elements. But they did start off as a carbon hydrogen structure, right? And that's why they would be classified as organic. Now, we talked about alkanes. So, right, those are the guys that have single bonds throughout, and they're chains of carbon atoms, starting with the simplest, which is just a single carbon. So obviously that's not a chain, but having single bonds only, and only carbon and hydrogen. So we went up till we drew the structures of methane, ethane, propane, butane. We talked about pentane and hexane. We talked about naming them. So the names for the number of carbons, and then the name for the family. All right, you put those two together and you get the name of the compound. And we tried that with alcohols, and we got those names over here. We mentioned saturated and unsaturated compounds. So saturated compounds are the ones that have single covalent bonds between the carbon atoms, right? Only single bonds, whereas unsaturated have at least one carbon to carbon double bond, right? It could be more than one carbon to carbon double bond. It also could be a triple bond between carbon and carbon, right? That's possible. But if there's only one of these, either a double bond or a triple bond, that is falls under the category of unsaturated, and that would be monounsaturated. If there's more than one of these double or triple bonds in the molecule, then that would be called polyunsaturated. For example, right, if you have something like this, right, and you add the hydrogens appropriate. So there are two bonds over here, so this guy can take two hydrogens. In fact, right, the hydrogens would be coming in here, top and bottom, and this guy already has three bonds, so you can only accommodate one hydrogen each, and then two, right? So this is some molecule, right? Let's not get into it. This is some molecule. It has two double bonds, so this would fall into the category of polyunsaturated. Similarly, this, right, that's a carbon-carbon triple bond, and so there's only space for one more bond with carbon, because the maximum number of bonds carbon can form is 4, and this carbon gets nothing because you can see it's forming 3 bonds over here, 1 bond over here, so that's 4. So there's no hydrogen coming in for this guy, and 3 hydrogens over here, right? And for the carbons, what you need to do is check the number of bonds. Is each carbon getting 4 bonds? Yes. And so even though this is a triple bond, right, there's only one of them, and so this guy is monounsaturated. Then we talked about the home. Yeah, question?
No.
Then we talked about homologous series, which is a series of compounds with similar chemical properties due to the presence of a functional group. A functional group is an atom or group of atoms that determine the chemical properties. So that's the guy who's taking part in the reactions. Alkanes don't have a functional group, right? Because they're saturated, they have single bonds, carbon and hydrogen only. So you don't really have a lot of reactions to talk about. The only two reactions mentioned in your syllabus, one is the combustion reaction, right? And so this is for methane. You can have the combustion reaction for ethane or propane or butane. You have to balance it out accordingly. And right, because the products will be the same. You can very well have towards butane, you've got, right, C4H10 plus O2, and you're getting the same products. right? So what you want,
Yeah.
right, you got 4 carbons here, so you put 4 over here, and that gives you 8 oxygens. So you're putting 4 over, well, no, that's giving you 8 and 9. Right, and how many hydrogens do I have? I've got 10 hydrogens here.
Yeah.
So 5 and 8. Hmm. 10 hydrogens, 4 carbons, okay. 5 oxygens and 8 oxygens. So 5 and 8 is 13. 13 oxygens. So I can get 12 by putting in 6. You know what I can do actually? Now
Right.
this is something that, right, it's not, what's half of 13?
Half of
7 point.
6.5, right?
Yeah.
So let's see. I've got 4 carbons over here, 4 carbons here. I've got 10 hydrogens here, right? I've got 10 hydrogens here.
yeah.
So that's fine. I've got 2 oxygens here, and then 4 twos are 8 and 5. 8 and 5 is 13. So what I can actually do is this.
Yeah.
I can do that.
Yeah.
Can
That's
you explain that again?
Huh?
Can you please explain that again?
Uh, what we try to do normally is, right, deal with whole numbers. Now, as I was like, okay, fine. So my carbon and hydrogens are balanced, but my oxygen is imbalanced because I'm getting 13 oxygens and 2 oxygens. So if I put in something else, right, I'll have to move stuff around a bit more. So, right, the balancing is going to get a bit complicated. Perhaps it's going to take a bit more time. So basically what I did, right, what I want is 13 on both sides, right? On this side, after balancing carbon and hydrogen, right, because there's oxygen with the carbon, there's oxygen with the hydrogen, so that's also being affected due to the numbers I'm placing with these two. And so I'm ending up with 13 oxygens, right?
yeah.
Over here I have O2. So whatever number I put with O2, so O2 and I put 4. So 4 twos are 8. So this will become 8. Knowing that, the number I want to achieve is 13. Now 13 is not an even number, so it's not, you know, a multiple of 2, right? So I have the option of either going for 6, which will give me 12, which is 1 less, or I can go with 7, which will give me 14, which is 1 more. And so in both cases, it's not going to be balanced, right? And so
Yeah.
what I can do is take 6.5, which can work. The reason why it can work is because O2 is diatomic, right? And so I'm just taking that part, right? So 6.5 times 2 is 13. And so in this case, it would be considered a balanced equation, right? Now, obviously, this is not the go-to thing, but yeah, it works, right? It's something you can do, and it is valid.
Okay.
Right now, just keep in mind that doesn't mean you can do any decimal. I'm taking like 4.32. No, like just like whole numbers or zero point 0.5, right? Not like any decimal,
Yeah. Okay.
right? Either fulls or halves. Okay, so the point is that any of these can be used for combustion, right? This is for butane, and yeah, the other reaction that they undergo is a substitution reaction with halogens, right? And that occurs either in sunlight or UV, and that's because sunlight and UV provide activation energy for the substitution reaction to occur. And so one of the hydrogens, right, now the example given over here is methane. Again, it could be any of those, right? You could very well do this for butane. So that's right. You're going to get HCl, which you're getting over here with methane as well. And what you're doing basically is you're replacing one hydrogen with a chlorine. So it was H10, now you got H9 and a chlorine. Right? This could possibly be done with fluorine or bromine as well. So you could very well have CH4 plus Br2, right, giving you CH3 Br plus HBr. Is this making sense?
Yeah.
Right, because chlorine, bromine, right, chlorine, they're all halogens. Sophia,
Yeah.
making sense? Are you following along?
Yeah.
Okay. On that note, before moving on to alkenes, what is the general formula for alkanes? Right? How did I know butane is this? Well, I could just, make the structure and count all of it, which is a long process, right? So for
Yeah.
hexane, I have to draw it out and then count, okay, there's 6 carbons, how many hydrogens are there? I don't know, count all of it. And so the general molecular formula, I'm focusing on molecular because later I will talk about uh, displayed formula and structural formula, and later on, right, we might come across skeletal formula. So those are all different ways of talking about the same thing, or diagrammatically representing the same thing. So what's the general molecular formula of alkanes, and that is CnH2n plus 2, right, where N is the number of carbons. So, right, butane is for 4 carbons, so that's 4 H2n. 2 times 4 is 8 plus 2, that gives me 10. What's hexane? 6. 6 2s are 12. 12 plus 2, 14. That's the molecular formula for hexane, right? Decane. Decane is 10. How many hydrogens are we going to have?
Mm. The can, right?
Just yeah, decane.
10.
10 hydrogens?
No, wait. 18?
Dude, look at the formula.
Oh, yeah. Okay. Wait, I gotta check.
22.
22, right? Dodecane is 12. How many hydrogens?
26.
6. Sophia,
Yeah.
following?
Yeah.
You seem sleepy,
No.
right?
This kind of tired.
Yeah, so just keep this general formula in mind for alkanes.
Okay.
Okay?
Yeah.
CnH2n plus 2.
Okay.
So any alkane they throw at you, or if you're not able to remember, oh, how many hydrogens go with this, just use this formula. Secondly, remember when we were doing bonding and structure back in chapter
Mm.
3, we talked about obviously ionic and covalent bonding, and so we also talked about we also did the dot and cross diagrams. Remember the dot and cross
Yeah.
diagrams,
Yeah.
right? So here I have CH4.
Uh,
Is this
I
an
have a question.
okay? Go ahead.
Like, how do we know that how many carbons are there? Like,
How do we know how many carbons are there?
like are they given?
Well, yes, you'll be given some information, right? Obviously,
Oh,
and right, if it's up till hexane, then you know it's up till six, right? Methane, so meth is one, eth is two, prop is three, bute is four, pent is five, and hex is six, right?
yeah.
If they just tell you, oh, what is the molecular formula for an alkane with 21 carbons, and you're like, we didn't study that. You don't need to study it. Just put it in the formula. You've got 21, right? 21 times 2 is what? 42, right? And 42 plus 2 is 44. Simple. That is the molecular formula. Does that answer your question?
Yeah.
Right? Have I studied something with 21 carbons? No. Do I know what it's called? No. Do I need to? No.
No.
Okay. So CH4, methane. Let's start simple. Let's keep it simple. Right? Is this an ionic compound or a covalent compound?
Covalent compound.
It's a covalent compound, right? Which means that the bonding is through the sharing of electrons, right? So if you are asked to draw the dot and cross diagram for CH4, what are you going to do? Right? Obviously,
We are gonna make it.
well, obviously you're going to make it, right? But you just need to keep that in mind of how to go about it. So I'm going to leave some space, right? Here's one carbon, here's another carbon, big enough, right? I'm going to draw space for smaller atoms of hydrogen. There's one, there's two, there's three for this guy. One, two, and three. I'm gonna do that one again. Right, and then I show the sharing of electrons. So that, right, one electron pair that is shared represents one covalent bond. Right? Oh, in
Yeah.
fact, this is I drew this wrong. Oh my bad. So
Like,
I'm not going to raise my drawing. Right? Let's just make this C2 and H6. Right? So this is, what is it? Ethane. Right? And so, right, they're all single bonds, and so, right, that's a pair of electron being shared with each, and you label them hydrogens all around and the carbons. And so that's a dot and cross diagram for ethane, right? And
Yeah.
similarly, if you're asked to draw a dot and cross for any of the alkanes, right? Methane, ethane, even propane. So you add another carbon over there, you adjust the hydrogens accordingly, right? And you show the shared electrons. Okay,
Yeah.
Haram,
yeah.
you're good. Okay,
Yes.
okay. Uh, right. So today we will start with alkenes, right? Now the name might be similar, but right, they are two different families of organic compounds, right? So this is another homologous series, organic compounds. Right, and these have one carbon carbon double covalent bond. Right, that double bond is the functional group of these guys, which means if they're going to take part in any reaction, right, it's going to be focused around the carbon carbon double bond. Right, and the general formula for these guys is CnH2n. That's it. Right, where N is the number of carbons. Any questions?
No.
No.
The simplest alkene is ethene. Right, so the ENE name is coming from the alkene, and the eth is coming from the number of carbons. So how many carbons would ethene be having?
1.
2.
Sophia, if
Oh,
there's
yeah.
if there's just one carbon, what is it going to double bond with?
Yeah, okay.
Okay, so one thing to keep in mind, right? It's a good thing you made that slip up. With alkenes, because it needs to have a carbon-carbon double bond, the smallest, the simplest alkene is going to be a 2-carbon molecule,
Okay.
right? You can't have anything simpler than that,
Yeah,
right?
okay.
So if there's 2 carbons, how many hydrogens is it going to have?
6.
How 6?
Like 2 to the 4 plus 2.
That is the general formula for alkanes. The general formula for alkenes is CnH2n. That's it. So how many hydrogens?
8.
Are you guys okay?
It will be 6 now. Like,
I mean, she's right, it is 6 though.
Can you guys see this?
Yeah.
Right? Follow the red dot. What does the formula say?
like, uh,
CnH2n.
yeah.
2N.
2 carbons. How many hydrogens?
2 2 carbons, right?
Yeah,
Like earlier you told us that it would be H2n plus 2.
that was for alkanes. Now
Oh,
we are
sorry.
we are talking about alkenes. This is different.
Oh, sorry. It would be 4.
Before, yes, miss 8 hydrogens,
Yeah, okay.
right? I mean, you cannot possibly fit in 8 hydrogens with 2 carbons at all. It's not possible. Right, so this is going to be
Like,
4.
what's the difference between alkenes and alkanes?
Okay, so let me first draw this out. So what is C2H4 going to look like? It's going to look like this. Two carbons, 4 hydrogens. Check the number of bonds each carbon has. 2, 3, 4, 2, 3, 4. Each carbon has 4 bonds with it, right? This is ethene, right? This is ethane, so that's an alkane. no double bond, all single bonds, saturated. This is unsaturated. There's a double bond between the carbons, right? Secondly, so that's one difference. Secondly, because the alkanes, so this is ethane, alkane, right? You can have methane, which is a single carbon. You cannot have ethene because, you know, you need a carbon-carbon double bond, right? You cannot have a carbon-carbon double bond with a single carbon. Get it?
Yeah.
Haram?
Yeah.
Okay. So the smallest molecule in the alkene family is the ethene with 2, right? And so we go up and we've got propene. What's the molecular formula of propene? What does prop tell us? How many carbons are there?
Uh, 4 or 3.
3,
Um, yeah.
right? So what's how many hydrogens?
6.
6. Butene, what's the molecular formula going to be?
Uh, C4
Hmm.
and H8.
Sobia, I need your response.
You
Pentene.
got it. You got it now.
Pentene. Sobia, right? Not to be confused with the shampoo. Okay? You find this at a chemical store and you'll, oh, shampoo, and it's not going to end well with your hair, right? So,
5
yeah, 5 carbons and
carbon, and the hydrogen is 10.
10, right? And hexene.
Hey, me? Should I do it?
Yeah,
6, and hydrogen is 12.
good. Right, now if we draw it out, let's draw out butene, right? So we've got 4 carbons. And so the question is, right, we know that there is one carbon-carbon double bond. Unless you are told otherwise, and I'm leaving this right for later, because when I talk about the displayed formula and the structural formula, I'm going to talk about something called isomerism. So isomers, right? So if you are asked to just draw out the molecule, right? Draw what the molecule looks like, Saina. So this is what's called the displayed formula anyway, right? Where do you put the double bond? So you put it at either end. Put it at the very end. Now, whether you put it to the left or the right, that doesn't matter, but put it at one end, right? So I'm putting it over here, right? And then
Yeah.
and then you fit in the hydrogen. So this guy is going to get 2 hydrogens. This guy is going to get 1 hydrogen only, 2 hydrogens again, and 3 hydrogens, right? If we were to draw
Uh,
hexene, for example, you've got 6 carbons. 1, 2, 3, 4, 5, 6. Where do I place the double bond? Again, just put it at the end, any one of the two ends, right? I'll put it here.
right. Oh,
It doesn't matter. It doesn't matter. Right or left doesn't matter. Just put it at the end, right? And then you fit in the carbons. Sorry, the hydrogens. All right.
yeah.
Are you guys following?
Yeah.
Yes.
Okay. Okay, so since we're doing this, right, instead of leaving this as suspense, this thing is called the molecular formula. Okay,
Yeah.
and this thing is called the displayed formula. This is a proper term, displayed formula.
Okay.
Okay, to be specific about this, uh, just a sec, sorry. Right, so the displayed formula for molecule, let me write that down. Of a molecule is a diagram that shows how various atoms are bonded and shows all the bonds. Right, in the molecule as individual lines. Okay, just read this on your own. Tell me if it makes sense or not. Looking at what we've done so far, right? So we've done these earlier as well, right? Yeah, over here. So does this definition of a displayed formula make sense to you?
Yeah.
Haram?
Yes.
Right? So molecular formula is just telling you how many of each atoms there are, right? In a particular, like, you know, molecule, obviously. A displayed formula is you actually drawing it out completely, showing, okay, fine, this comes first, this comes next, this comes next, and then showing each bond. So a straight line, that one line is showing a covalent bond, right? It's showing all the bonds in the molecule as individual lines. So over here, there's a double bond. So I'm drawing two lines. So each line is representing one covalent bond. That's why earlier I told you if there's a triple covalent bond, I would be drawing three lines, right? And that's as high as covalent bonds go, right? Single, double, or triple.
Yeah. Okay.
Clear? Now we'll get into this. Perhaps we'll talk about this a bit more later, but right now you know molecular formula and displayed formula. Clear? Any questions so far? Any, and hopefully all's good.
Yeah.
Okay. So what we're going to talk about next for alkenes, right, is right. Let's draw a dot and cross for ethene. So we've got C2H4, right? And so here's my carbon, here's my other carbon, and here's a hydrogen, another one here. So, well, no, I'll label them with black. right? And so there's a single bond between the carbons and hydrogen, so there's only one pair of electrons being shared. And there's a double bond between the carbons, right? And so what you have is dot cross, so that's this pair, because the dot and cross represents the electron coming from each atom. I could just make 4 crosses, but technically it doesn't matter, right? But it does, because the dot and cross tells you, oh, one electron is coming from one atom, right, and the other is coming from the other atom, and so that shows the sharing. That's why it's dot and cross. So one dot cross pair shows one pair of shared electrons, so that represents, right, one dot and cross is one covalent bond. Right, and so because there's a double bond over here, I'll have 2 dots and crosses. But I'll draw it dot, cross, not cross, cross, and dot, dot, showing the pairing, and so that represents one covalent bond. And then I label these. And so when you're drawing these dots and crosses, just give yourself enough space in the intersection to actually fit these in. All right. So that is the dot and cross diagram of
Yeah.
ethene. Now let's talk about some reactions.
Okay.
Achha, the book gives you a table of the melting and boiling points of ethene, propene, and butene, and they're all gases at room temperature, right? So that's in the book. You can just take a look at it. Structural isomerism is something I'll talk about later with the structural formula, right? And so getting alkenes. So alkenes need to be produced in either labs or industries, because they are not naturally available. Right? There are very few alkenes that are found in nature. Okay, and so what happens is, to get alkenes, they employ or use a process known as catalytic cracking. Catalytic obviously means they're using a catalyst. Cracking basically means breaking or splitting. So what they do is that they take larger, right, and less useful alkanes, right, and they split the molecule. And so what you get as a result of that reaction is you get a smaller alkane plus an alkene. Okay.
Yeah.
So instead of saying smaller, I guess better to say shorter.
Shorter would be making much more sense when it comes according to height, wouldn't it?
Length, not height.
Yeah.
Yeah.
So you're talking about the length?
Yeah. So
Okay.
again, I wrote larger over here, so longer. So you take a longer alkane, and then split it, and what you get is a shorter alkane and an alkene, right? And right, so in catalytic cracking, the what you call it, the catalyst used is aluminum and chromium oxide, right? So this is the process. Let me show it to you. They're taking an alkane called dodecane. So dodecane is for 12. So 12 and 26, right? And this is a gas. And they are breaking this up, and it's giving you C10H22. So that's decane plus ethene, right? Which is C2H4, right? And all of these are gases. Alternatively, you could also get something different, right? Same reactant, same starting material. You've got C12H26, and what you could get is possibly, right? A possibility is C8 and H18 plus C4H8, which is butene. And this is, right, octane, right? So oct for 8, and it's an alkane, so octane,
Yeah. Okay.
right? So what they're doing, as you can see, they're taking a longer alkane, and the temperature used is about 550 degrees centigrade, and you are using aluminum or aluminium and chromium oxides.
Yeah. Okay.
These are the catalysts, right? Okay. And
Yeah.
sometimes in these reactions, hydrogen gas may also be produced. Whether or not it's produced depends on the reaction conditions. All right. Are you guys actually
Yeah.
following?
Yeah.
Are you sure?
Yes.
Okay. Now, right, this is something that's done in industry. They mention that this process can also be done in a school laboratory. In that case, it is called thermal cracking. Why?
And
Because,
by thermal, I can guess it's like
By the way,
heat.
the catalyst fasten the process.
huh?
Haram,
Sorry,
go on.
Thank you. By the way, catalyst like fasten up the process now.
speeds up. It,
Oh,
it,
okay.
it, it speeds up the reaction by lowering the activation energy, providing an alternate route for the reaction
Okay.
to occur, right? A lower energy pathway for the reaction. It, right, it causes the reaction to occur faster, so to speak, right?
Also, by thermal cracking, can I guess that it means like heat breaking?
Well, yes, you are splitting an alkane
Okay.
using heat. Now, this is something done obviously on small, because you're doing this in a laboratory,
Yeah.
right? Possibly in a school laboratory as well. And so in this case, right, you are taking an alkane, and you are heating it, and you are using glazed pottery. Sorry, it's unglazed pottery, sorry. Broken unglazed pottery as a catalyst. Broken unglazed pottery as catalyst. And so if I just show that to you in the book, right? The diagram that they've given for this. It's here, right? So you've got this piece of wool that is soaked in paraffin. So paraffin is an alkane, right? I mean, that's the name given to one of the alkanes. So it's not the chemical name, it's the common name. And so it's going to give off fumes, right? From that wool, it's a gas. It's going to give off fumes, uh, and then you have this, right, porcelain, right? So that pottery, you're providing heat, and so over here the paraffin is going to break up into a different alkane and alkene, and so, right, it's going to come in here, go back, right, through this. So there's a cold water and then a crystallizing dish, and then the alkene will be collected over here. All right.
Yeah.
Yeah.
Right now, the chemical reactions that these take part in, and then followed by talking about polymerization, and then structural formulas and structural isomers. We'll probably have to leave that for our next few classes. Right? Hopefully, we can get this all done next week if we sort of manage our time properly. All right. Any questions,
Mm.
Phobia? All good?
She
Oh,
has like already left the class.
oh. All right. So see you next time then, inshallah.
Allah Hafiz.
Allah.